Hello everyone, welcome to my channel. Today we are going to learn about binary search algorithm in details. Along with that, I'll talk about auxiliary space and its relevance in case of binary search. Also, I'll discuss about the common bug in case of calculating the mid-index of a divide and conquer algorithm, specifically when you are dealing with huge amount of data. So, let's begin. So before jumping into binary search, let us understand how a normal search, rather linear search works and why binary search is coming into picture. Okay. So let us take one example first. Suppose you have this array where we have few data 10, 5, 23, 56 to 34, 12 and you have been asked to search for a data for one element 34. Okay. Normally what you do, you will first start traversing through the array. So first will come to the first index, means 0th index will match whether X matches with the first element of the array or not. Does it match? No. Then the second one 5, it matches? No. Third one, fourth one, fifth, then sixth one matches. As this array is a very small one, so the way we are traversing the whole array and searching for our required element is okay, because in linear search what happens, the number of operation depends on the number of element. See, if here we have number of element is how much? 7. Suppose n is the number of element in one array, so n equals to 7 here. So number of operations will be also 7. Okay, n number of operations, so number of operations will be 7 only. Now you have to understand when this n will be more than 7. Suppose you have somewhere 1 lakh data. In that case, the number of operation will be 1 lakh, right? If you have 1 lakh data, in that case, number of operations will also be 1 lakh in the worst case scenario. Because imagine that your 99, this number of element means the last element, obviously 0 to this much in case of 1 lakh data, right? The index will be this, and imagine that your required or the element you are looking for is the last element of the array, or even worse, like the element is not even there in the array. In that case, we have to go to each and every element or each and every index to search for our required element. So in that case, what happens in linear search, we have the complexity of big O of n, right? So according to the number of data where you have 1 lakh data, our complexity will be big O of 10 to the power 5, means big O of 1 lakh, right? So the cost will be huge. So how to optimize this? In this case, binary search provide you the optimization. That's how you can, that's when you should use binary search to optimize such searching algorithm. Now let us understand how binary search is providing that optimization. We are getting that performance optimization. How? Okay, before that, you should always consider that binary search algorithm you can only apply on a sorted array or sorted search structure, which means whichever search structure you are using right now and you are trying to apply binary search algorithm, you must sort the array first, then apply binary search algorithm. That's a prerequisite for binary search, which is not there in case of linear search. Okay. Now let us understand how does binary search works. Let's take one array first. I have taken this array. See, this array is sorted 2, 5, 10, 23, 34, 56, 101. Okay. What are the steps? First, what we need to do? Target middle element of the search structure. Okay. Now, see, this is my middle element according to the index. There are 7 elements: 0, 1, 2, 3, 4, 5, 6. Now, this is my mid element. So, very first thing is you have to get the mid element first. So, you got the mid element. Then what you need to do? Then check if your search element matches the middle element. Now, let's imagine that you have to find 56 here. Your search element is 56. Okay. Now, does it matches? 56 is 23? No. Right? Okay. Then what we'll do? Then we'll check if the search element is less than middle element or not. What is our search element? 56. Less than 23? No. So, we will be going, then consider only the first half of the structure. Else consider the second half. So, in our case, 56 is greater than 23. So, we will be considering the second half of the structure. Then what we should do? Repeat from 1 to 4 means again target the middle element, check if your search element matches with your middle element, or if the search element is less than middle element, then consider the first half of the search structure, else consider the second half of the structure. So this is the basic algorithm of how binary search works. But let us understand programmatically. Okay. Okay. Let us suppose now you have your L means your lowest index at 0. Okay. We are starting to understand this binary search programmatically, how it works. So let us imagine that you have one lowest index L at 0. You have your highest index at 6. Okay. Now you have, if you want to get the middle element of your search structure, you have to calculate the middle index using this lowest and highest index. What I am doing is L plus H by 2. Okay. L plus H by 2, 0 plus 6 by 2 equals to 3. We got the middle element. Okay. But here is a trap, or here is the bug. You should not use L plus H by 2 while calculating your mid. Why? Because it will fail if your low plus high is greater than your maximum positive integer value, which is 2 to the power 31 minus 1. Suppose you have a huge amount of data, somewhere like 1 lakh or 1 million, something like that. Okay, so in that case, your lowest and highest index will be much more than the 0 and 6, quite obvious. So in that case, if your low plus high greater than your maximum positive integer value, which is this 2 to the power 31 minus 1, in that case, the sum overflows to a negative value. And when you are dividing that negative value using 2, that value stays negative. And that's where in case of C, it will give you array index out of bound and with some unpredictable results. Okay, and in case of Java, it will throw you array index out of bound exception. And that is why you should always use L plus R minus L divided by 2. See, if we are applying this here, so 0 plus 6 minus 0 divided by 2 equals to 3. So the data would be same. Just for your better understanding, this part you need to divide using 2. Okay, so this is how you should consider while calculating the index of your mid element of your search structure. Although this bug has been there for quite a few time actually. Then this bug got resolved and we like developers, and they came up with this way that yes, before specifically in case of like merge sort or divide and conquer algorithm, we should always use this particular way while calculating the index of your mid element of your search structure. Okay, let's move on. So we got our index of our first mid element as 3. Okay, now let us check whether 56 is equals to the element present in this third index or not. What is the element? 23. Does 23 matches with 56? No. So what is there? 23 is less than 56. So what we'll do? That is why we need a sorted algorithm. We need a sorted search structure here, because here now we will be considering based on 56 is greater than 23. So we will be considering only this much of array or search structure whichever you are using currently. So we will be considering this. Okay. So what we'll do is, now your lowest index will be pointing to, instead of this 2, it will be pointing to L. Okay, now your lowest index L will be pointing to 4 and your highest index will be H only. Okay, I mean highest index H will be pointing to 6 only. Okay, so here is the catch. Two things. If your search element which you are trying to search does not matches with your mid element, then you will have to check whether your search element is greater or less than your mid element. If it is less than your mid element, in that case your lowest index will be similar as it was previously. Your lowest index will be this only. Okay, and your highest index in that case will be mid minus 1, means the element just before your mid. And that is where again I am repeating this, and that is why we need a sorted search structure to apply binary search. Okay, and in our case, which is the second case, that if your search element is greater than your mid element, then in that case you should consider the second half of your array. Okay, and in that way your mid plus 1 means the element just after mid will be your lowest element, and then highest index will be same. Okay, so this won't be the mid element anymore. Okay, now we'll check what is the mid element. So L is right now at 4th index. H is right now, so this is, how come this is 4? This is this has become 4 by L equals to M plus 1. What was M before? 3 plus 1 equals to 4, and highest will be same as before. Okay, so now we are considering this much. So obviously now we have to calculate M as well according to our new part or new half of the array. Okay, so we will be calculating now what is the M previously. So we'll be considering this way. What is L? 4. What is your H? 6 minus 4 divided by 2. What will be the data? 4 plus 1, which will be 5. So your mid is 5. Now your M or mid is pointing to 5. Okay. Now again, as we are pointing to the mid element, now again we'll check whether our search element matches with that mid element or not. Does it? Yes. See, 56 we are searching for, and our current mid element is also 56. So we got our element, right? We got the data that we are looking for. So this is how binary search works. But here is one thing. In case of binary search, you can apply this binary search algorithm in two ways. One is iterative way, another one is recursion way. Okay, so I'll show you the code applying both, like using both of the methods. So, and one more thing is, in case of binary search, the time complexity is big O of log n, and that is why even if your number of element in your search structure is suppose 1 lakh, like the one we have already seen in case of linear search, where the number of operations was 1 lakh and time complexity was also big O of n, so obviously big O of 1 lakh, which was much more in case of performance cost. But here what happens? Here, as n is 1 lakh, so obviously this way big O of log n, how much it would be? So big O of 1 lakh or 10 to the power 5, it will be somewhere 16.63. So this much number of operations we need to do for 1 lakh data. You can imagine the difference, right? There for 1 lakh data you have to do 1 lakh operations, but here you have to do 16.63 number of operations. So there is a huge difference. So obviously it is optimizing the performance of your search algorithm in a huge way. Okay, so now let us go to the code right now. Okay, so using iteration, this is the code. Let us understand it. So I'm having one class here which I have named it as binary search using iteration.java. Okay, here I have taken the similar array 2, 5, 10, 20, the similar data that I have shown you. Okay, and we are trying to search for the element 56. I'm creating the object of this class here so that I can access the actual method where the binary search is coming into picture. So what I'm doing here, first of all, two things I'm passing. One is array, another one is the element that I'm trying to search in that search structure. Now what we need to do, first we need to get those two indexes. In our case, obviously L will be 0 always, because lowest index will be starting from 0 of a search structure or array. In our case it's array. Then the highest index will be array dot length. Array dot length is nothing but it gives you the length or size of your array. But your index of your last or highest element will always be -1 from the size or length of your array. So that is why this. Then first how we'll loop it through? We'll check whether our last element is less or equals to highest or not. Then only we'll be looping it through. Okay. Now the thing, but why we are making it equals to, I'll come to that part a bit later. Now let us understand first this. as I have already mentioned that your medium or your mid element, mid index, you should calculate always with this way, L plus H minus L by 2. And similar way, as I have already mentioned in the algorithm, if your mid element array M is the index of the mid, so array M is equals to X, then you should return that mid elements index. It means you should return M. Else, if your search element is greater than your array mid, then our lowest index will be mid plus 1, means the next element of mid. Okay, else if your array mid is greater than X, okay, then what it should be like, the highest element. Obviously, if this is one array, if this is the mid element and your search element is greater than this mid element, then we should consider this. If your search element is less than your mid element, then we should consider the previous one. In our case, 56 is greater than the mid element, which was 23. In our case, mid element was 23, 56 is greater than 23. So we are considering this part. Okay, and that is why the debug point or the trigger will be coming to this part, and our lowest element or the lowest index will be pointing to right now M plus 1, means to 34. Else, if suppose we are trying to search 5 here, then in that case your lowest will be same, but your highest will be mid minus 1, means 23 was your mid element, which was 0, 1, 2, 3. 3 minus 1, it would be 2, or 2th index element, which was 10, it would be. Okay. So now it will come to this, and we got lowest as 34 and highest as 101, and again it will loop it through as the while. See, according to the while loop condition, L is less or equals to H. So in our case, L is 4, H is 6, right? So it will be again come here, and it will check for the mid. According to the mid will be getting as 5, which is 56. So obviously this condition will match, and it will return 5. It will return 0, 1, 2, 3, 4, 5. Yes, the 5th index it will return it. Okay, but what if you are searching for 34? What happened then? In that case, your 56, when the mid element it got as 56, obviously it won't match, because in that case you are searching for X equals to 34. In that case you are searching for X equals to 34. So what happened then? It means the element you are searching is less than the mid element. It means that it will come to this part. Array mid is less than X. No, your X is 34 then. So in that case, array mid is greater than 34. If you are searching for 34 in that case. Okay. So in that case, your 34 is less than 56. So which is coming to this part. In that case, your H will be M minus 1, means M, what is M right now? M was 5. So 5 minus 1 equals to 4. If you see here, previously L was also 4. Now H is also 4. And that is why we have given this condition that even if your lowest index is equal to your highest index, still you should loop it through once to check whether that particular element. So actually in that case, your lowest, your highest and your mid all will be pointing to 4 only. Okay. So 4 means the 4th index means you got 34 when you are again looping it through. Okay. So that is why we are putting this L less or equals to H. Okay, now let us run it to see whether it is working or not. See, element found at index position 5. So similarly, I have done the binary search using recursion. So in case of recursion, we have to keep that in mind. Recursion is nothing but you have to call the same method again and again. Okay, so what happened here is, see, that is why we are passing array, the element we are trying to search, the lowest element at the beginning and the highest element, highest index, not lowest element, lowest index and the highest index. And here in the code, what we will be doing is, see here the first part is similar to how we have done in the iteration. Okay, it will be checking for all the things and everything is similar. But when it is seeing that your search element is greater than your mid element, so instead of there changing the lowest as m+1, we are calling the same method again by just passing the lowest one as m+1. Okay, and in case your search element is less than your mid element, we are passing the highest element as m-1. That is the only difference in case of, like, this is the difference of how the when you are coding binary search using recursion, that is the main difference. Because recursion means you have to call the same method again and again. So the method is calling itself. See, the binary search method is calling itself. Okay, now let us run this also. See, element found at index position 5. Because we have taken the same array and we are searching the same element here as well. Okay. But here one thing to mention, that in case of when you are using binary search using iteration, both of them, in case of both of them, in iteration method or recursion method, time complexity is same, big O of log n. But the auxiliary space in case of it would be big O of 1. Let us understand why. See, when I am saying that in case of iteration, the auxiliary space, I am talking about auxiliary space. What is auxiliary space? It's nothing but it's part of space. When you are calculating space complexity, it is mostly about the input size that your program is taking. Okay, but auxiliary space is part of that space complexity only. It is just that extra space or temporary space that your program or method will be taking. Okay, so in case of iteration method, when we are doing the binary search using iteration method, that is big O of 1. Okay, because we don't need any extra spaces while we are doing the binary search using iteration. But when we are doing it using recursion, if you can see here, every time the method is calling itself, right? So when this method, suppose first we are calling this array 5606. So the array that we are trying to look into to search for the data 56, the lowest element is 0, highest element is 6. Then again it will be calling itself, as it didn't got the data at the very first time. So it will be calling again binary search array 56, lowest is now 4, highest is now 6. Suppose the data was not in fifth element, the mid element, then again it will be calling it as fourth array. And suppose the data was less than the mid element, which was at fifth element, so again it will be calling as array 5644. So here in this case, here I mean this line is calling itself again and again, or this line, it is calling itself again and again, right? So that is where it is adding this method every time in the call stack, and that is where it is using the extra space. Okay, and this is why the auxiliary space getting utilized in case of binary search while using recursion would be big O of log n. Okay, so that's it for binary search. That's all for today. Thank you so much for watching this video. If you like this video, then please do like, share and subscribe to my channel. It means a lot to me. I'll catch up with you guys in my next video. Till then, keep learning with pride.